Yesterday we looked at exponential functions. Today we're going to look at the inverse of that. We're going to look at logarithmic functions. This is in Chapter 4. So if we're going to talk about logarithmic functions, I first need to discuss what a logarithm is. Probably many of you already know this, but let's review it. We're talking about real numbers here. We're not going to work with logarithms when we have complex numbers. So if we have positive values for our constant a and our variable x, and we don't want a to be 1. Just like with the exponential function, a is going to be a base, and we don't want that base to be 1, because anything you do to 1 just winds up being 1. So we're going to restrict a not to be 1, but we want it to be positive. We can't work with taking logarithms of negative numbers. We can't be complex, we can't be negative. What we have is that y is the logarithm of the number x, and when you're talking about a logarithm, you must say what base you use. So this is the logarithm with respect to base a of the number x, and that's true if and only if x is equal to a raised to the y power. Now notice this is that exponential function we looked at yesterday, where you have a number raised to a variable. The base is this thing here. The logarithm is that exponent. So a logarithm is an exponent. Logarithm is the exponent that you raise that base to in order to get the number. So if I want the logarithm of the number x, and I want it in base 2, then what I'm asking is what power would I need to raise 2 to get that number x? So this is an exponent, this is a base. If you look at it this way, this is the base, this is the exponent. X is the number we're getting that logarithm of. Or x is the number we will get if we raise that base to that power. Some examples. In base 2, the logarithm of 8 is 3, because if we take 2 and cube it, what do we get? We get 8, right? So the logarithm in base 2 of the number 8 is the number 3, because it's the exponent we have to raise 2 to get the number 8. We can have fractional bases. The only restrictions is our base has to be positive, and our number that we're taking the logarithm of has to be positive. So we can have a fractional base. We can take the logarithm to base 1/2 of the number 16. Doesn't matter what base we have. It can be anything. That logarithm happens to be -4, because what it says is if I take 1/2 and I raise it to the -4 power, I get the number 16. Because remember, negative exponent, what it means is flip it over. So this is like taking 2 to the 4th power. And what's 2 to the 4th power? 16. So the logarithm of 16 in base 1/2 is -4. Logarithm of 100,000 in base 10 is 5. And so forth. As long as your base is positive, and as long as the number you're taking the logarithm of is positive, then they will always exist. You cannot take the logarithm of a negative number. You cannot use a negative base. Logarithm of 1 is 0, because no matter what base we have, if we raise it to the 0 power, we're going to get 1. So that's some examples of logarithms. That's how they work. This relationship between the definition of the logarithm and this base raised to an exponent is a very important relationship that's going to be necessary in order to solve equations involving logarithms. So this situation where if you have this, then this has to be true. It's also going to be that if you have this, this has to be true. We'll get to that a little later. So we can now do things like put our variable as the base and get an equation of that type, where what is the base that if I take the logarithm in that base of the number 16 over 9, I will get minus 2. In other words, what base, if I raise it to the minus 2 power, will give me 16 over 9? That's actually how you work it, is you take the base, whenever the variable is the base, you rewrite it in this other form. You take the base and raise it to this power and set that equal to the number here. Now we have an equation we can solve. We can't solve that equation that has logarithm in it because there's no technique to do that. But convert it to this exponential form, and we can. X to the minus 1/2 is 1 over x squared. Cross multiply and solve. And here, take the square root of both sides. You get plus and minus 3/4. However, x is our base. And remember I said we cannot allow a negative base. We have to throw away that negative answer. So our solution is x equals 3/4. That's the only answer we can keep, because you cannot allow a negative base. This is the process when you're looking at a logarithmic equation like this. To solve it is you convert it to the exponential form, because that eliminates the logarithm. We could also have our variable be the number we're taking the logarithm of. Previous one, our variable was here in the base. In this one, our variable is the number we're taking the logarithm of. We're still going to do the same thing because we can't solve a logarithm. So we're going to convert that to the exponential form. What would this exponential form look like? Take the base, 16, raise it to that power, and set that equal to that number. 16 raised to the 3/4 power equals x. Now all we have to do, since we have x equals, all we have to do is work out the arithmetic there. This is one of those places where you need to know how to raise a number to any exponent. So make sure you know how to do that on your calculators. This one you could do with exponents and radicals and actually do this manually. You get x equals 8. So in base 16, the logarithm of 8 is 3/4. Third type. Now our variable's over here. So we looked at a variable here, we looked at a variable here, now we look at a variable here. In this case, all you do is evaluate the logarithm. That requires that you know how to take logarithms on your calculator. You'll actually have two buttons on the calculator for logarithm. One will say log, the other one will say ln. Talk about that in a minute. But here, if you calculate this on the calculator, this one you can also work a different way. This is a way which will work occasionally. When you rewrite it in the exponential form, you wind up with the same base here and here. This is 6 raised to the 1/2 power. This is 6 raised to the 2x power. 6 squared raised to the x, which is 6 to the 2x. And one of the things we said yesterday was that if you have a to the b equals a to the c, that means b equals c. If I have a situation like this where the bases are the same, then the exponents are going to equal each other. So that means 2x equals 1/2, or x equals 1/4. But you could also get that by the calculator. Some of these, if it has the right form, you can work out with paper and pencil, but most of them you're going to need that calculator to do. So I would just stick with the calculator. Yeah. Well, you can't actually put a base 36, but we'll see how to work with that. And I don't know if we get to it. I think we get to it today. But yeah, you're on your calculator. I'll go ahead and bring it up now. There are 2 buttons on your calculator. One says LOG, one says LN. LOG is for base 10. LN for this base E, that number we talked about yesterday. Those are 2 very, 10 obviously is a common number. E is so common it's also been put on the calculator. And those are the only 2 the calculator does. So what if you have a base 36? We'll see in a little bit something called a change of base theorem, which allows you to calculate something like that using base 10 or base E. But rather than talk about it now, let me get to it, but that's a little bit later. And see, this is one of those special ones that I said, it's only going to work occasionally. It's not a necessary thing to know if you know how to use the change of base theorem. You need to know how to do change of base. So if it's an either or, learn change of base rather than this. Okay, logarithmic function. We have some restrictions. We have to have our base greater than 0, not equal to 1, and we have to have the number we're taking the logarithm of be positive. So the base and the number have to be positive, and we can't have the base be 1. Our logarithmic function then is f of x equals logarithm of x. But it's a logarithm with respect to some particular base. That's logarithmic function with base a. And it's different answers if you use a different base. So you must specify what base you're using. Exponential and logarithmic functions are inverses. We talked about inverses yesterday. If you take 2 inverse functions, if you calculate one function, use that to go into the other function, you'll get back to where you started from. That's what inverses do. So the exponential function we looked at a couple of days ago and the logarithmic function we're looking at today are inverses. And in fact, those 2 equations we looked at a minute ago, logarithm base a of x equals y and a to the y equals x, well, that a to the y is an exponential equation or an exponential function, and the logarithm is the logarithmic function. And we mentioned when we were talking about inverses that the domain of the inverse is the range of the function and vice versa. So the domain of an exponential function is a set of all real numbers, therefore the range of the logarithmic function is a set of all real numbers. The range of the exponential is the positives, therefore the domain of the logarithm is the positive. That's the restriction I mentioned a minute ago, is you have to have the number you're taking the logarithm of be positive. This is a statement of that fact. A domain of your logarithmic function is positive numbers. So we can only get logarithms for positives. Here is what a logarithmic function looks like. So the basic function is logarithm base a of x. Just like we did the basic function y equals x and y equals x squared and y equals x cubed. This is f of x equals logarithm a of x. A has to be greater than 1 for this particular one. We have either a greater, as long as a is greater than 0, it works. But there are two different shapes to the function, depending on whether you're above 1 or between 0 and 1. So we're going to look first at the one where we're greater than 1. And if you just pick your base to be 2, just to have some numbers to calculate with, because it does make a difference which ones you're looking at, you'd get a table like that, and if you plotted it, you'd get a curve that looks like this. So this is the shape you'll get for the logarithmic function when a is greater than 1. And it has some similar type of behavior to what you saw in the exponential. It has an asymptote, and it goes through certain points. Now, this is the inverse function of the exponential, so it's not going to have the same asymptote or the same points, but it's similar. We're going to always go through the point 1, 0. The exponential went through 0, 1. This goes through 1, 0. This is going to go through the point a, 1. The exponential went through 1a. This goes through 1 over a and minus 1. It's for a greater than 1, it's an always increasing function. It's continuous. It does not exist for negative inputs. So it only exists for positive inputs. You can only have an x be a positive number. You can't take the logarithm of a negative. The domain is 0 to infinity. You can't take the logarithm of 0 either. So it's a 0 to infinity in parentheses. The range, as you can tell from the graph, is minus infinity to infinity. That is exactly the inverse of what an exponential was. And in fact, the curve is the exponential curve, but it's been shifted around, flipped over and shifted around. That's what happens. If you remember inverses, if you drew a diagonal line up here, the inverse function is going to be the mirror image about that diagonal line. So increasing continuous over 0 to infinity. Y-axis is a vertical asymptote. As it gets close to the y-axis, it's going to go to negative infinity. Always passes, no matter what the base is, it will always go through those points. Always 1 and 0. So you can pick any base you want, and it's going to go through the points 1 and 0. Now let's do the same thing when a is between 0 and 1, so a fraction. So if you use 1/2, you get values like this, you graph it, the function looks like this. It's still only in that positive half. You never take the logarithm of a negative, but now instead of increasing, it's decreasing. As x gets bigger, the logarithm gets more and more negative. Always goes to the point 1, 0, just like if a is greater than 1. Always goes through a and 1. Always goes through 1 over a and minus 1. So it doesn't matter what the base is. The graph is going to go through 1 and 0. It's going to go through a and 1 and 1 over a and minus 1. This is a continuously decreasing. It's continuous. The domain is 0 to infinity. The range is minus infinity to infinity. Y-axis is a vertical asymptote, but now as you get close, it's going to go to positive infinity rather than negative infinity. F of x equals a to the x. The inverse of that is g of x equals the log to base a of x. If you remember that direct relationship, that the logarithm of this is true if and only if that's true. So the logarithm of a to the x equals a number is true if and only if the number equals a to the x. So these are theoretically inverses of one another. And because we have a base a, I can't plot a base a on this tool I'm using. So I use the change of base theorem. Change of base theorem says if I want the logarithm in some unusual base, take the logarithm in something I know and divide it by the logarithm of that base. When I go to the graph, that's what it shows here. Here's my exponential. Here's my logarithm. This logarithm is actually logarithm base 2 of x. And that should be the inverse of that. Well, here's the exponential, here's the logarithm. Here's my diagonal line. They're definitely inverses. You know, they're mirror images of each other. As I change my base, it's at base 2 now. So I change my base. They continue to be mirror images. So this just illustrates that exponential and logarithm are inverse functions of each other. And just like before, any point here would have the mirror image point over here. So 0, 1 is going to have 1, 0, and so forth. So that's what the logarithmic function looks like. When you're working with equations that have logarithms in them, sometimes you will encounter situations where you either can make the equation simpler by breaking that logarithm apart into more and then working with multiple logarithms, or sometimes it would be better if you combine them all together and make a single. Unfortunately, that's possible with these logarithmic properties. There's a product, quotient, and power property. If you think back to exponents, you had a product, quotient, and power rule for exponents. Logarithms are exponents. So we have the product, quotient, and power property for logarithms. For logarithms, what it says is that if you have the product of two numbers, the logarithm of that product is the sum of the logarithms of the individual factors. So the logarithm of xy is the logarithm of x plus the logarithm of y. If you have the quotient of two numbers, the logarithm of that quotient is the difference of those logarithms. Logarithm of the numerator minus the logarithm of the denominator. So product is add, quotient is subtract. And remember, you have to subtract in a very specific order, top minus bottom. If you have the logarithm of a number raised to a power, then you can take that exponent and bring it out in front and write it as that exponent times the logarithm of the number. So you can either take a product and break it apart, or you can take two logarithms that are added together and combine them into the logarithm of a product. And similarly for the difference and the quotient and the power. So stated in words, you have it this way. Logarithm of a product is the sum of the logarithms. Logarithm of the quotient is the difference of the logarithms. Logarithm of the number raised to a power is the power times the logarithm. And a couple of additional things. The logarithm of 1 is always going to be 0, and the logarithm of whatever base you're in is always going to be 1. That's true because whatever your base is, if you raise it to the 0 power, you get 1. So the logarithm of 1 is always going to be 0, no matter what base you're in. Likewise, if you raise a base to the first power, you just get whatever the base is. So the logarithm of the base is 1. So just as an example of applying that product rule for logarithms, let's just take two numbers. I know you can multiply 8 times 6 and get the number 48, and then you could take the logarithm of 48. But just to show the illustration, you could also take the logarithm of 8 and add the logarithm of 6 to that, and you would get the logarithm of 48. You can actually verify that on the calculator if you're so inclined, where you can do that. Now, round off may get you a very small error, but it would be down in the several decimal places before you'd see it. But that's the idea. So you can take an expression like this, and because it's a quotient, you can use the properties to break that into a difference. Now you no longer have a division going on. What you have is a subtraction, and that might be easier to work with than the division. It depends on the problem as to whether it's important. One critical thing you need to make sure that you're doing is, in all cases, the base remains whatever the base started with. If it's a base 6, then it remains a base 6. You do not change the base in the middle of the problem. We'll get to a change of base later on, but that's a very specific operation. If you're just using these logarithmic properties, you do not change the base. If you're given something like this, where you're taking the logarithm of a root, remember that a radical can be changed into an exponential form, where you have a fractional exponent. Once you have an exponent, you can use that power rule and bring that exponent down, and so then you're just working with the logarithm of the number. In science and engineering, frequently you will encounter some fairly complicated relationships between variables, and logarithms can help simplify combinations and solutions of those types of equations by being able to take logarithms. Logarithms also are useful when you're graphing, because they compress a scale dramatically. I think we looked at it earlier, the sound intensity. Did we look at that already, where we did problems with sound intensity? No, we haven't looked at that. We'll look at that later. But it uses a logarithmic scale. If you know what the Richter scale is for earthquakes, that's a logarithm, so that the difference between a magnitude 7 and a magnitude 9 is like 100,000 or something. It's a big difference in actual size of the earthquake. So what that does is, if you had a number that went up very quickly, taking logarithms compresses it back down until it's a more it highlights the small stuff at the small end, but doesn't lose the information at the big end. So it's very helpful in some of those situations. If you have a very complicated combination, just do it a piece at a time. We have products here, so we can break that into sums. We have quotients, so we can break that into differences. We have powers, so we can bring that down. So this one, the way it's being done is, we're going to first, let me illustrate it this way. Think of this as being the logarithm of base b of rs squared t minus the logarithm in base b of u cubed v to the 5th. If you did this step first, that's the quotient root property of logarithms, where I take this minus this. Then I can use the product rule on this and break it into this, this, and this. And I can break this one into this and this. That's the product property. I did both of those steps in one. Then I can use the power property to bring this down in front here, this down in front here, and this down in front here. And now this is completely simplified from what we started with. That's one way these properties work, is to take a combination and break it into individual pieces. You can go the other direction too. I guess I'm continuing here. Same sort of thing. Still doing this breaking apart. With the radicals, convert first to exponential. So this could be converted to all of this raised to the 1 over m power. Then you use the 1 over m times the exponents in here, and that gets that. That's conversion from radical to exponential. Then take the logarithms of everything, and you could wind up with that. And could be, for some situations, that's a better form to work with something in than trying to work with it in this form. The other one is if you start with logarithms added and subtracted. You can compress those all into a single logarithm using those rules in the reverse direction. A subtraction means I'm going to divide, and an addition means I'm going to multiply. These are independent of one another, so it's not I'm going to subtract that whole thing. I'm just going to subtract this one. So I'm still going to have this times this divided by that. Only if there's a parenthesis around the two logarithms would you divide both of them. If you have have multipliers in front of the logarithms, convert those to exponents on the bases. Do that first, then use your addition and subtraction properties to combine into a quotient and a product. So here I would change the first term. I'm going to take the 1/3 and I'm going to make it an exponent on x. I'm going to take the 2/3 and make it an exponent on y. Now I don't have the multiplier here anymore, but now I have the sum of these, which means I'm going to multiply this times this, and I'm going to divide both of them by that. Then I could, if I wanted, I could write the fractional exponents as radicals. One thing to be very careful about that you do not do, you cannot break apart a sum, only a product or a quotient. So do not try to simplify this type of thing. The logarithm of a sum remains the logarithm of a sum. Do not break it apart. Okay, because of the relationship between the logarithm and that function a to the y equals x, that thing we looked at a few minutes ago, where if you have the logarithm of x, then that's like having logarithm of x equals y, that's like having a to the y equals x. Because of that relationship, if you raise a base to the logarithm of a number, then you get the number. A to the logarithm of x gives you x. And similarly, if you take the logarithm of a base raised to a number, you get the exponent. So a to the logarithm of x gives you x. The logarithm of a to the x gives you x. Those are just relationships that come out of the definitions, and so, but they are useful when you're trying to solve equations. Here's an example where you could do something with it. This is not a very useful example, but it does show the effect. If you have a number and you're raising it to a power, and that power happens to be the logarithm of a number, and it's the logarithm in this base. So logarithm, what that is that says what power must I raise 7 to get the number 10. That's what logarithm means. What power do I raise the base to get the number? So what power would I raise 7 to get the number 10? Well, if I have that power and I raise 7 to that, I get 10. That's all it's saying. What power do I raise 5 to get 5 cubed? Well, I'll raise it to the third power, right? 5 cubed is 5 cubed. I raise 5 to the third power to get 5 cubed. What power do I raise r to get r to the k plus 1? I raise it to the k plus 1. So pretty straightforward, but it will be useful in solving logarithmic equations.